Hi everyone. So in this reaction we're going to do an electrophilic aromatic substitution reaction of vanillin. Alright, so this molecule right here is vanillin, and we're going to add an iodine to this at position 5 and make iodovanillin, if you will. So this stuff smells like vanilla, and it's a compound with an aromatic ring, so we can do an electrophilic aromatic substitution. And what I want to do in this video is go over some of the things that you're going to need to do in order to perform this reaction successfully. I am not going to flat out calculate the theoretical yield for you or anything like that, because you should be able to do that at this point. But I am going to go over some stuff. All right, the first thing is we're starting with 1 gram of the vanillin compound. All right, and we're going to use sodium iodide as a source of I minus, and then we're going to add this compound, which is bleach, and that bleach is going to turn this iodide I minus into actually I2 and then I plus. Okay, so that's basically what we're going to do in this case. And in this case, we're going to add 1.17 grams of this. Now, you're going to need to know that the molar mass of this compound is 152.15 grams per mole. The molar mass of this compound is 149.89 grams per mole. And the molar mass of this compound, the vanillin, is going to be 278.04 grams per mole. The other thing you're going to need to know, because it will come up because you're going to do the melting point to test your product, is the melting point of this compound is about 180 to 184 degrees C. All right, so using this information, you could find the number of moles of this, and then for every 1 mole of this, you get 1 mole of this, and then you can find the number of grams of this that you're going to form. You can do the same thing with the NaI. You can find the number of moles of NaI. For every 1 mole of NaOI, we're going to get 1 mole of this, and you can find your limiting reagent and theoretical yield in that way, as you have done many times before. Now, there are some very important things that we need to be aware of here. The first thing is that when you're adding the bleach, okay, this is just sodium hypochlorite, which is bleach. It's in bleach. Bleach is about a 5% solution of this. Stuff you put in a pool is about 10% solution of this. So this is just a bleach molecule. All right. When you add this, you need to add it slowly, and you need to be patient. The other thing is that your reaction mixture is going to turn a reddish brown kind of color. That reddish brown color is coming from I2. I2 is not going to be successful in an electrophilic aromatic substitution reaction because I2 is not a very good electrophile. We actually need to form I plus, which is your good electrophile. So it says in the lab manual that you need to stir it after you've added all of the bleach slowly. You need to stir this for about 10 minutes. Now, if your solution is still a brownish color and not a yellowish color, when you've a reddish color, so if it's a red brown and not a yellow, you're going to want to keep stirring it even if it's more than 10 minutes. Better to wait a little bit longer than to stop the reaction after 10 minutes and turn out that you have I2, and I2 is definitely not going to add over here, and therefore you're not going to have very much of your product. You're going to have mostly just your starting material. All right, so that is very, very important. All right, so practically, here's what we're going to do. All right, the first thing is we're going to do is we're going to add our 1 gram of vanillin to our round bottom flask, okay? And this is going to be a 100 milliliter round bottom flask. Then we're going to add 20 milliliters of ethanol, and we're going to stir it to dissolve all of the vanillin into the ethanol. All right, once the solution is clear, we're going to add our 1.17 grams of the sodium iodide into here, and we're going to stir until the solids are completely dissolved. We're then going to take that flask and we're going to place it into a ice bath like this and cool it to 0 degrees. So, cool it for 5 minutes or so. All right, we're going to have a clamp, of course, holding this flask. All right, so we're basically going to stir this and cool it down. Make sure you dissolve it and then cool it down. After This is nice and cool, 0 degrees Celsius. We're going to have our separatory funnel up here attached to a ring, and in here we're going to have 11 milliliters of bleach. This is the same bleach you'd use for laundry, okay? Then what we're going to do is, over a 10-minute period, we're going to slowly drop her, one drop at a time, add this. Note, when you're slowly adding this, what you don't want to do is add a bunch, wait a couple minutes, add a bunch more. Ideally, you have this at a consistent slow drip such that it takes about 10 minutes for this 11 milliliters of bleach to transfer into the stirring cooled flask down here. Okay, then what should happen is you're going to go from kind of a pale yellow color to a reddish brownish color as you add this, because you're forming I2 on the addition of the bleach. So the I minus is going to turn the I minus, the bleach is going to turn the I minus into I2. Then what you're going to do is, after you've added all this over 10 minutes, you're going to take this thing out from the ice. You're going to allow it to warm up to room temperature, and you're going to continue to stir. In this case, it should go from the red-brown color, the iodine, back to a yellowish color, because in that case, we are basically getting rid of the I2. It's turning into I+. It's acting as our electrophile, and it's making our iodo vanillin. Okay, so that is basically the plan for this. The key here is to be patient. So you want to add this slowly over 10 minutes as this turns a red-brown color. After you take this out, you want to stir it at room temperature for 10 minutes. If it's still kind of red-brown and not really yellow, allow it to stir for more than 10 minutes. Maybe you have to stir it for 15 or 20 minutes. You're not going to have to stir it for 4 hours, okay? So basically, you want to try to get the reaction to go as much as it possibly can. All right, so once the reaction has completed, then we're going to go to the workup step. And the workup step here is extremely important because it can be dangerous. So what we're going to need to do is we're going to need to add hydrochloric acid to this reaction mixture, okay? And if you remember, what does this reaction mixture have in it? Well, it has excess bleach. We're using a very large excess of bleach here. If you add hydrochloric acid and bleach, you make chlorine gas. Chlorine gas is extremely poisonous. So we don't want to make chlorine gas. We want to destroy the bleach before we make the chlorine gas. To do that, we're going to add sodium thiosulfate. Specifically, we're going to use 10 milliliters of a 10% weight by volume sodium thiosulfate solution. That will destroy the bleach. Again, you have to add sodium thiosulfate before you add the hydrochloric acid, because if you don't, you're going to make chlorine gas and it will bubble out, and if you breathe that in, that's bad. Okay, you're going to do this under the extractor arm to be safe, okay, but you're also going to make sure that you add the sodium thiosulfate to destroy the bleach first, because you don't want to be breathing in the chlorine gas. Then what you're going to do is you're going to use 5% hydrochloric acid added in 1 milliliter portions. You're going to test the pH each time using a pH paper, and you're going to wait until it turns acidic. Okay, then once the solution is acidic, you're going to start to see the precipitation of this iodo vanillin compound right here. Okay, and this will start to be a white precipitate as you add enough HCl and water to allow this to precipitate. Make sure that you continue the precipitation for at least 10 minutes. So again, it's about being patient. Just because you see a little bit of precipitation as soon as the you start to add the HCl doesn't mean you're done. Continue to add the HCl until it's acidic. It should take about 6 milliliters of that 5% solution to get there. Okay, and also make sure you wait at least 10 more minutes after you've turned it acidic to make sure that your precipitation is complete. So you have a lot going on here. The most important thing is we destroy that bleach with our 10%, about 10 milliliters of our 10% sodium thiosulfate solution before we add the HCl, because bleach and HCl makes chlorine gas, and chlorine gas is poisonous. Also, again, just remember when you're back at the beginning stages, make sure that you get rid of all that I2, make sure you stir long enough so that your solution is no longer red-brown. So it's a little confusing because it basically you add the bleach, it turns red-brown, then you take it out of the ice, and then the red-brown goes away. So that's what we want to happen because we want to form that I+. So I want to go over a couple of things, including the separation scheme and the mechanism, and I want to talk a little bit about how you're going to measure your product. The first thing is the separation scheme. So let's talk a little bit about the separation scheme. So the separation scheme, as you know, begins after the reaction ends. So we should theoretically have our 5-iodo vanillin being present in the solution. We're going to have some bleach, okay, that's in there. We're going to have ethanol, because that's what we used as our solvent to make this reaction work. We're going to have some water in there, okay, and we're going to have some I2 slash sodium iodide, some kind of form of iodine in there as well. All right, after this, what we're going to do is we're first going to add our sodium thiosulfate, which I've said several times because it's really important. This destroys our bleach. Then we're going to add HCl until acidic. And if you remember, it should take somewhere around 6 milliliters of this, but you could just test it with pH paper to make sure that you have an acidic solution. What we're going to hopefully do is precipitate our 5-iodo vanillin. All right, so remember that this compound is going to precipitate relatively quickly after the addition of the HCl, with of course the sodium thiosulfate before that. However, you still want to let it continue to precipitate for 10 minutes to make sure that you get a good yield. This reaction is all about being patient. It's not a super technically challenging reaction, but there are a couple of safety concerns, and you just have to be patient. You're adding things slowly, you're waiting as long as it takes, not necessarily as long as the lab manual says. In this case, the 10 minutes should be good, but in the previous case, you might have to stir for a little bit longer, as we talked about. All right, and we're going to end up with an aqueous layer, which is going to have whatever the bleach turns into, which when you add the sodium thiosulfate is going to be sodium chloride. All right. You're also going to have some excess sodium thiosulfate potentially. All right. You're going to have your ethanol, your water, and at this point, you should have iodide. Whoops, I made the I twice. Iodide. Okay, because the sodium thiosulfate will turn I2 into iodide as well, and I realize you can't see that. All right, so this should be your precipitate of your solid. You're going to want to dry this as much as you can, so let the vacuum filtration to suck all the water out, let it sit on the vacuum filter, for a good little while, depending on how much time you have left in the lab. You might be working on your separation scheme, or you might be working on your post-lab questions, and just let it sit there because you have time left. Okay, then you're going to measure its melting point. The drier it is, the closer you're going to get to this 180 to 184, especially when things have this high of a melting point away from water. If they're wet, it's going to be significantly different from this, so you want to dry it as best you can. Okay, so this should be our separation scheme. The next thing that I want to talk about for this reaction is actually the mechanism. Okay, the mechanism of this reaction. And the mechanism here should focus on not the formation of the I+, but the I+ as an electrophile. So the first thing I need to do is draw my vanillin, which is going to be an aromatic ring, okay, like this. All right, and it has an OH here. It has an ether group here, and it's an aldehyde here. Okay, and if you remember, we have this carbon 5 and this carbon 6. So we're going to focus on these director groups. So if we look here at this molecule here, this molecule here is going to be an ortho-para director, right? Because this is an activating group. So it would direct here, here, or here. This is the only spot that's not blocked. This one is also an ortho-para director. So this one would direct here, or here, or here. So it will direct to this spot. Okay, and this molecule here, now we have a partially positive charge on a carbonyl carbon. This is a deactivating and a emetic directing group. So it would direct here or here. So the most beneficial spot is here. Now you would have some direction towards here, this being an ortho director. Okay, you'd have almost no directing towards this spot right here. But in this case, you would have some direction here from this one. This one is not really good because it's a deactivating group, so it doesn't want to go to this spot. And also there's some steric hindrance here. Iodide I plus is a large electrophile, so we're going to focus on this spot right here. So what do we have? Well, we have this I plus, which again, you don't really need to know about how this is formed. This is formed, with a redox reaction with the bleach. All right, so this is going to get attacked by the ring like this. And we're going to end up with some resonance forms. All right, so this is a quite large molecule, so you have to kind of draw it out a bunch of times. So you have an OH here, you have the ether group here, and you have the aldehyde group here. Okay, so I just redrew this with the same groups, all right, that we have. This double bond and this double bond, nothing happened. All right, we now have the iodine attached to what we have labeled as carbon 5. That means that this now has a positive charge. But as you've probably seen before, you can resonate these positive charges in rings. Specifically, that double bond can move over like so. And what we end up with is the ring. Again, I'm just redrawing all the groups. And the aldehyde up here. All right. Now, this double bond, nothing happened. We now have the I here as well. All right, this double bond, nothing happened. This one moved up here. You now have your plus charge on this carbon right here. Okay, I'm drawing them inside the ring. A lot of times they're drawn outside the ring. I don't think it really matters, but just be aware of that. If somebody prefers to draw it inside or outside, I don't know that that matters. All right, so then let's do one more. All right, this time, this double bond moves. It doesn't look like an arrow, really. Okay, so this double bond moves over like that. So I'm going to redraw the ring. This time I'm not going to forget the iodine. So the iodine goes there. All right, the OH goes there. The ether goes there, and the aldehyde goes there. So I just redrew all the substituents. This time, this double bond just went along for the ride, so I'm going to redraw it. This double bond moved here, and now we have this plus charge right here. And if you recall, there's lone pairs on this oxygen, and this can stabilize that positive charge, making it favorable for the iodine to add in the 5 position. So this is where we're going to preferentially get the iodine. Now, it doesn't really matter, okay, which one of these things that we draw, but I haven't drawn it yet. There's a hydrogen in here in all cases. So what's going to happen? Something is going to come along, some kind of base, water, whatever, and it's going to grab this hydrogen, okay, so that this hydrogen is going to leave these electron pairs to go in there. And this is because aromatics are very stable. So we want to reform the aromaticity. So some kind of base, okay, water, ethanol, it could be anything. None of these are particularly strong bases, but they're capable of grabbing this proton. And what we end up with is the aromaticity being reformed. So we end up with this becoming a double bond. These electrons come in here like so. We end up with the iodine here, the OH here, all right, the ether here, and the aldehyde here. So this is our mechanism of this reaction. So before I go, I want to talk a little bit about how we're going to analyze our product, and that'll be the last thing. So as we talked about before, one way we're going to analyze our product is by melting point, and we're basically going to precipitate it with the addition of the sodium thiosulfate to destroy the bleach, and then the HCl we're going to precipitate, we're going to let it sit for 10 minutes, and we're going to dry it for as long as possible. Then we can measure the yield and the melting point. Okay, so those would be two ways we can measure how much did we get and what is the melting point of what we got. The other thing we're going to do is IR, but IR here is a little bit not helpful. All right, let me explain why. Well, let's look at what we're going to see in the IR. The first thing we're going to see is this carbonyl peak somewhere around 1700 in our starting material. The problem is our product has this same carbonyl peak, so they're both going to have that peak around 1700 centimeters to the minus 1. Let's look at another peak you might see. You're going to see these CHs, okay, these aromatic CHs just above 3000. These are present in both the starting material and the product. You're going to see an OH here, which is a broad peak, somewhere around 32, 3300, something like that. These are present in both molecules. We're also going to see a CH3 here and a CH3 here, which is going to be an aliphatic CH, okay, just below 3000 centimeters to the minus 1, but we're going to see it in both molecules. So the IR here is not super descriptive, although it's good because it has a bunch of peaks in it, so you can identify the peaks and get practice. It's not a great way to distinguish these two molecules. NMR would be far better, but with several hundred of you running NMR on all of these is just a practical problem. Okay, we can't run NMR for all of these, so that is basically that. You'll have an opportunity to do that